Hi, welcome to week number 10. We made it. We are now on dry friction. And in this topic, the key will be to first understand the concept, and the concept is happily enough, the concept is not really too far from what we see in real life all the time. So it's very close to us. And one of the key points to succeed in this topic is the ability to draw good free body diagrams. Now, if this is something that we have been struggling with, this is the time to now go back and then do a few more examples, because success in this topic depends heavily on you being able to visualize and draw and identify all the forces that act on rigid bodies. So friction appears when you have two bodies that are in contact with each other, right? Now, this is a force that occurs at the point of contact. Now, this force resists sliding between the bodies, right? And is known as friction, right? So, in the most common case that you may be thinking is maybe a box over a floor, and then you are pushing with a load P, right? And there is some resistance, and then we would call it friction, right? This is the concept that more or less will come to us. Now, there are several categories of friction, and friction is a really complex problem, and there are many theories about the friction that happens in different situations. Now, three broad categories of friction are presented next: fluid friction, dry friction, and internal friction. Now, these two, number one and number three, that won't be the focus on this course, right? The one type of friction that we'll discuss in this course is this one, the dry friction. This is the one that we will see as part of ENG 130, right? But it's convenient to revise what is this big picture of friction forces. Now, fluid friction, number one, right, is a frictional resistance that exists between two bodies when a lubricant, usually fluid, is sandwiched, right, at the point of contact between the two bodies. Now, this is very complex, right? And then you see it all the time in a car engine, right? You apply oil, and then you apply oil so it lubricates the parts and prevent them from actually having wear and tear, right? So they last longer, right? You know what happens when your oil is leaking, right? Your engine can actually get damaged really soon, right? Now, there is friction, right? Because this liquid is going to be sandwiched between these two surfaces, and it is going to transmit some of the forces. So, and this, it's a complex phenomenon, right? And it varies with the velocity, the pressure, the temperature, and the viscosity of the fluid, right? It's quite a complex problem, and in particular, the temperature aspect of it has to be accounted. You don't want this oil to boil, right? For example, in a joint that is bad, you don't want it to boil. So it's particularly important for the thermal analysis is particularly important, right? Now, you'll see this in future courses, maybe a heat transfer course for those of you going into mechanical engineering. Dry friction, number two, that's the one that we want, right? That's the one that we will be investigating here. And it says, right, exactly what we're trying to envision at the beginning, right? It's you or us trying to slide a box over a surface, right? Now, here they suggest dry concrete floor. There is no lubricant, so it's dry surfaces, right? Dry surfaces means dry surface, dry friction. The resistance to sliding, and you can visualize, right? You can visualize the fact that if you're trying to push this box, you will find a resistance, right? A friction force that will resist the movement, right? That resistance to sliding is called dry friction, right? Dry friction. It's relatively simple to understand and calculate, right? If we use the appropriate model. Now, this phenomenon is really complex, but one of the most simplified models that give good results, right, over a considerable range of variables, right, is the model is a model in which the friction force, right, the friction is proportional only to the normal force. And you may see that this is quickly, right, if you think, well, the friction force is it different in a cold day than a hot day? So temperature, so many other factors they are playing a role, right? But the model we'll use, and the model that you may have actually become familiar is when the friction force is proportional to the normal force only. In the normal force, right, the normal force is the force that appears, right, appears. This is the P applied, this is the friction force. And the normal force is a force that appears, which is perpendicular, right? This force is perpendicular to the sliding plane. Right. So the normal force will be right, related to the weight of the box, right? If we want to create the full free body diagram of the box, so you may see that the heavier, right, the heavier the box, right, the more friction you'll have, right? So if the body is heavier, right, you will agree with me that you will have a big normal force, and then the friction force has to increase, right? So this is captured by this equation that says that the friction force is proportional to the normal force. The heavier the object is, the more friction you will have opposing the movement, right? And then mathematically, right, that proportionality, we take it into account just by saying that the friction force is equal to some coefficient of friction times the normal force. Now, this model, you may remember it even from high school, right? We got to use it a number of times. And then we will be investigating this case extensively in this set of lectures, right? This is just an introduction, and then we go to the third type of friction, right? Internal friction. Now, internal friction is a phenomenon that happens at the molecular level, right? Essentially, it's one molecule, right? A body is made by millions of molecules, right? And then is the grinding between molecules, right? All that grinding between them, right? All those contact, these molecular forces between these components, they make up the internal friction. Now, one quick example is, for example, to imagine that you have a bar made of steel or wood or plastic attached to some strong surface, and then you apply a force, right? You pull one end up and let it go, and then you will start at some deflection, and over time, right, all those deflections will be becoming smaller and smaller until, right, if you let time pass, right, a period of time sufficiently long, you'll see how the movement stops. And then the question will be, right, why did it stop? And you may say, well, there is some resistance in the air, and obviously that dissipated some of the force. Yes, but these bodies will also stop moving at the vacuum, right, when there is no air. So there is something internal to the body. So that dissipation of energy is due to the friction between the contact forces between the molecules, right? By grinding among each other, right, these contact forces will dissipate energy, right? Will dissipate energy through heat, right? And they will dissipate energy in form as cracking, right, and other damage mechanisms, as sound even. And then that is how the initial energy you gave the object, right, when you pulled it up, right, dissipates, right, due to the internal friction mechanisms, right? Now, this is again quite a complex process, right? And you will see some of these on your classes on vibration, right? Mechanical and civil engineering, they have these internal friction topics. Now, going back to dry friction, right? The box sliding over a floor, right? So why does that friction, right? Why does that friction appear? Or what is the friction force? What is that friction? Now, if we take a microscope, right, and we look at the contact between the two surfaces, right? If we assume that this is moving towards this direction, and then the bottom surface moves towards the left, you'll see that there are a number of contact forces, right? A number of contact forces that will be created. And you may also see that according to the geometry in this figure, right, it's easy to see that points D, right, just because of the geometry, right, entirely by coincidence, points D and E, right, they don't develop contact forces. So some points, when you try to slide this box left to right, some of the points of these are rough surfaces that have many points of contact, but some of them engage, and some of them they don't engage, right? When you reverse the sign of the movement, right, when you push the box on the other side, then the other points of contact will engage, perhaps. So all in all, right, if you have just a small body with a few points of contact, you will see that the friction force is not the same in one if you push from one end to the other than if you push from the other end to the one end, right? But if you have a large body, right, such as the ones that you have in real life, right, it doesn't matter because the differences, they will be small, right? There is roughly the same amount of point of contacts in average in either of the two directions. Now, so contact forces between the points of contact. They are equal in magnitude, but opposite in direction, thanks to Newton's third law, right? And then what we discussed, right? When we change the sign of the movement, those contact forces will switch, some of them, right, and to other points of contact, right? So forces generated at contact points, where the relative motion causes local interference, A, B, and C. Right, and if we reverse the movement, right, we may engage a different set of points. For example, in this case, D and E. For a typical body, right, there are a roughly equal number of contact points in the two directions, right? Now, things that we can notice here on dry friction, right? Take a look, right? I'm just going to go back, right, and then take one of these forces. Let's take force C. I'm going to take this upper force here and reproduce it here. So I have my contact force in the upper surface C, right? And you see that I can easily define two components, right? And I can do the same for all the upper forces. Right, all the upper forces, I can break them down into components. What about this one? So, right, I can break them down into components, and I can do the same with the lower forces. Right, so I can break all these forces into components. Right, so everything broken down into components. Now, right, for a perfectly smooth surface, only the vertical contact forces exist. So, right, if things were perfectly smooth, right, the point of contact, right, is just happens horizontally. So there will be only vertical components, right, vertical components. Now, real surfaces are rough when viewed through a microscope, right? So the general contact forces, right, generate horizontal and vertical components. This is what a real contact point will do, right? It will have two components. Now, the beautiful thing about that, right, is that if you add all those vertical components, right, plus the weight, you will get the normal force, right? And if you add all those horizontal components, including the applied load, you will get the friction force that you are looking for. Now, obviously, we won't go and measure all these forces at all these points, right? That's why we have theories, right? We have theories about that. How does that look like, right? This friction problem using free body diagrams. I have a free body diagram here, right? It's the box sitting on a surface, right? In this case, the floor, and I have some forces here. And if you really want to make this precision, right, I am illustrating only the forces acting on the box. There is, for example, there is an equal set, right, of forces on the floor, right? But I am illustrating in the drawing on top just the forces acting on the box, right? So at the beginning, right, I apply, right, I'm going to try to show what happens when I go from an applied axial load from 0 to the maximum point until I make this box slide, right? So when P is equal to 0, right, obviously there is no friction force, right? There is no friction force. The box will not move, right? The box will not move. Now, I am going to gradually increase, right? Gradually increase the force P, and you see how interesting things will start to happen, right? Now, I am going to make a small increment on the force, right? But if that increment is small, right? If I just push a little bit onto that side, if I make this P really small, I see that the box will not move, right? It will stay at rest, right? So for a small force, the box will not slide. Now I have to maintain equilibrium all the time, right? The box is not moving, so I have to have equilibrium. The sum of forces in X has to be equal to 0, right? So why is it that the box doesn't move, right? Why? Well, because the friction force is just enough to resist sliding, right? To resist sliding, but no more. The friction, right? The friction force is enough for the box to not move, right? And then I have that the applied force is equal to the friction force, right? You may be thinking, well, we defined friction as the coefficient of friction mu times the normal force. So I see friction as a single value. Well, this is one of the things that we have to change in our minds, right? The friction force is just this force laterally, right? This guy over here. And it can have a value of 0, or it could have the maximum value, right, just before the box starts to slide. So the friction force doesn't stay just constant, right? It depends on the applied load. And it could be, right, if this is P is 1 kilonewton, the friction force will be 1 kilonewton, provided that the box doesn't slide, right? If P is equal to 10 kilonewtons, then F equal to 10 kilonewtons, right? Let's assume that the maximum friction force is 100. So the maximum friction force just before the box starts to slide is equal to 100 kilonewtons. Well, then this force can increase to 40, right? Applied force 40, and then the box won't move, right? It will move only if P reaches 100 and exceeds 100. So the concept I want to start presenting to you is that the friction force will stay there, right? It will appear once you start applying load, and the friction force will take many values, right? And it's only when it reaches its maximum value that the box will start sliding, right? So the friction force is just not one static value, right? Just not one value. So so for F equal to P, right? F equal to P. So what happens if we keep pushing, right? So eventually we will make the box to slide, and that is when we have reached the maximum value for friction, right? We call it the static friction, and then we calculate that maximum friction or the static friction as the coefficient of static friction, right? Coefficient of static friction times the normal force, right? And then you may actually remember that these guys, right, they are given by tables, right? These guys are given by tables. Right? So what the tables are showing you is the maximum friction force that two surfaces can develop, right? Not all the values that the friction could take, but just the maximum value. Just before the box slides, right? Just before the box slides, the friction reaches this value, right? Mu s is the coefficient of static friction, and n, as before, is equal to the normal force. Now, right? This is a very important result, right? Static friction, right? Static friction. That is the first formula we are going to investigate. By the way, right? All we need is this extra formula. The rest of the equations we need to examine friction problems we have already, right? Sum of force in x equal to 0, sum of force in y equal to 0, and sum of moments will be equal to 0. Right? So we have all the tools we need. We just needed this equation here, right? So that will allow us to tackle friction problems. So the coefficient of static friction, right, can be found in tables, right? Tables published by in books or manuals, right? And then the higher the static friction coefficient, the higher it is, the more friction you'll have. So solids on rubber have the highest friction, and metal on ice, right? So you're skating on the ice, you see that you just glide because the friction is just so small, right? So you see some values here that will present you values, typical values for this guy. But remember, this will allow you to get the maximum friction only, right? Mu s times the normal force, right? So these values will allow you to get that maximum friction. Now, and once the box begins to slide, right? If you are imagining this, right? Imagine you are pushing this box and it's very heavy, right? So close your eyes at home, close your eyes. But you're not closing your eyes. Please close your eyes. How did I know that you, well, anyway. Close your eyes. You're pushing this box and this box is very heavy, right? This box is made of wood. It looks like a container, and maybe there is a dinosaur inside the container, and you're pushing that container. And the box doesn't move, right? And then you push and push and push more and more and more until you start moving the box. Now, at that point, you may be aware, or you may notice that now to keep moving the box, you require less force than needed to start moving it, right? And then, the friction force is the same, mu times the normal force. So if you require a smaller force, that means that once things start moving, you are not using mu s, right? But a different value, right? And that different value is the kinetic, that is the static friction coefficient, and this is mu k is the kinetic friction coefficient. It's a bit lower, right? A bit lower than the static friction coefficient. You see here the static equilibrium, right here, sliding, and then this is the maximum friction force, the friction force. So when it reaches the maximum value, you start moving things, right? And when you start moving, you have to use a different friction force, right? The kinetic friction force, which is equal to mu k times the normal force, as opposed to the static friction coefficient times the normal force. You see, it's a bit smaller, right? A bit smaller. So sliding friction. Fortunately enough, we are not going to deal with cases in which there is movement involved, right? Luckily enough. So just to summarize, what are the sort of problems we will be investigating? Well, three basic problems. First one, no sliding. No sliding. So the friction force hasn't reached the maximum value, right? The force attempting to cause the body to slide does not exceed the maximum friction force given by F max equal to mu s times the normal force. To satisfy equilibrium, the friction force generated must be less than the possible maximum. So mathematically, it's expressed like this, right? Expressed like this. This is the first case that we will investigate. So quite a number of these cases, right? In the case, we have to assume, if we are not told, we have to assume that the body is not sliding. Or we assume that things are about to slide. They are not sliding and they are not moving, but the motion is impending, right? It's about to happen. So what happens just before it happens, right? In this case, the body is just on the verge of sliding. The maximum possible friction force is being generated, right? This means that the friction force is equal to F max, and the friction force, of course, is defined as mu times the normal force. So this is the second case, right? When things are about to slide. In some cases, we'll see, well, the body is not even close to sliding. Or in some examples, we will see that, oh yeah, the body is about to slide. And then I think my numbers are, well, then the third case, which we won't investigate, is when things are sliding. So this one we won't do in ENG 130. It happens, but we won't examine what happens in ENG 130. This means that we are pushing with the friction force equal to the kinetic friction coefficient times the normal force. So we saw that we said that we won't investigate things that are movement. So this case, you will have to wait until you have a future course to investigate what happens, right? Now, case number four is something that we will be doing quite a bit in this course. Checking for the possibility of tipping, right? Tipping. So we must test for this case. Tipping, which is rotation, of the body may happen in any of the first two cases, when the friction force is less than F max and when the friction force is equal to F max. We have to check if it happens before you reach the maximum friction force, right? Or at what point does it happen? Does the body slides before it tips over or rocks? Does the body tips over before it slides, right? So before we take a look at this guy, just let it dream for a bit. Imagine you are pushing this gigantic wood box over ice, right? Okay, ice. The box is made of wood. You push it on top of ice. You may feel that you can do it, right? With just a little bit of force, you can start sliding that box over the ice. So you didn't require that much force. Now imagine you are going to slide the box over a what is made of a floor made of rubber, right? So maximum friction force. What about a yoga mat, a gigantic yoga mat? You see, those are made of rubber and they have some textures, right? Quite nice. But now you have your box resting over a gigantic yoga mat. So what happens, right? When you push and push and push, you would agree with me that some of you, depending on what sort of box you are imagining rightly that this box won't actually slide. You actually will rock it, right? Your box will actually, right, start tipping. So how does that look like? Like this. The box will start tipping, right? And then may actually even rotate and fall over onto the other side. So same as what it will happen to this guy, right? So tipping. Well, I spent like 2 hours doing that animation, right? And then I thought it would be awesome. It was kind of anticlimactic, right? Anyway, so this possibility could happen as well, right? And you may think, well, if this guy is very, very heavy, right? Quite heavy, possibilities of tipping him over there are not many, right? Now, if this guy is very tall, you're sitting on that chair, right? And if you push on top, right, you may be able actually to make it fall. Now, the bottom line is that tipping will depend on the geometry of the situation you have with your rigid body, the amount of applied force, the weight of the object, and the surface condition. So we'll have to check all of this, right? Now, well, let's talk a little bit about what happens to the forces that appear on real bodies. So here is my box, right? And this is the free body diagram of the box, right? No, forget about the floor and all the forces acting on the floor. This is just the box. And then you see familiar forces. You see the load P here. You see the load P. You see the weight of the body, mg, and it just happens to pass through the center of weight of this center of mass of this body. Right? You see the friction force. These are all acquaintances of yours. And then you see the normal force. And then the normal force is offset a little bit from the position you may be expecting it to be. Right? It's a bit off, and it's not wrong. Right? And the thing is that it's not wrong. And it just so happens that the normal force has to move a bit to preserve equilibrium. Right? We will be taking a look at that case in a few slides when we do the rocking check. But just to kind of show you that indeed that normal force has to move, right? I want you first to imagine the case in which there is no load acting on your body. So the weight acts here at the center, and the normal force is aligned with the center of mass. Right? So imagine rocking is going to happen. Right? Imagine rocking is going to happen. So this box is actually lifting a bit, or about to lift, but you get the idea, right? So it's about to lift. So that means that the only point of contact is the corner. Well, the weight is still in the center of mass of the body, but you see the only point of contact is at the corner, so the normal force is actually here. You see? So yeah, the first thing I want to show you is that normal force moves, right? Of course, where would it act if not at the contact point? So the fact that the normal force moves has to be accepted, right? Otherwise, how would things rock? Right? There is always a point of contact. So the normal force can move and will move. Right? So the easiest way to visualize that is when the body is rocking. But you don't need the body to rock to see how the force, the normal force needs to move. I have a case here in which the actual load P is applied here at the top, and I have some weight, which I can call W, right? The weight of my body. So P is different than 0. It has some value. It is not enough to make it slide, but it is different than 0, right? And then you have to think about not only the equilibrium of forces in X, right? The friction force, or the equilibrium of forces of Y, which requires the presence of the normal force, right? To balance the weight and to balance. But you have to think about the equilibrium of moments, right? Now, if you think about the equilibrium of moments, right? If you choose a point to do your calculations, right? Let me just go back here. If you think of a point to do calculations about, right? If you take moments about the center of the box, right? So take moments about this point. You will find that the load P, right, has a moment which is clockwise to the body. The weight causes no moment because it is now passing through. I mean, we are taking moment just at the point in which the weight passes. The friction force, right? The friction force creates moment about the center of the body, which is also clockwise. So what resists the moment, right? Because it's not immediately that when I apply that force, the box will start to rock or to tip. No, it stays in equilibrium for a little bit until I increase the load for a bit. So the only way I can resist this clockwise moment caused by P and F is through the normal force changing or being offset or moving a bit from the load of the initial orientation, right? If the normal force moves this way, now it can create a counteracting moment, right? A counteracting moment to P and F, right? So the normal force has to move, and it will move. So in this particular case, right, I am illustrating the normal force as having moved already, right? So it's not something strange, nor something that should make you worry, right? So I have in the bottom of the box, I have, this is the weight, mg, and this is the load P, and this is the normal force, a bit offset, and this is the friction force. So I have two forces acting at the bottom of my rigid body. And these two are components of a resultant force, which I can write as this one here. So this is, right, both the normal force and the friction force is the contact force that we were seeing when we did the things microscopic. Well, the angle of that resultant force, right, can be obtained, right, easily as, tangent of the angle is equal to, right, F divided by N. And then if F is the, in the limit, right, the friction the coefficient of static friction times the normal force divided by the normal force, then the angle, right, the angle is equal to the coefficient of static static friction. So let's take a look, right? Let's take a look. So yeah, so at the limit, right, if the friction force is equal to the maximum value, we can define, right, we can define the angle theta is as the tangent of the angle is equal to the coefficient of static friction, right? And this is a very important result. If you wanted to calculate that angle, right, that angle, which by the way we are going to call the angle of static friction, right? If you want to calculate the angle of static friction, you just just solve for the angle like this. This is the tangent inverse of the friction coefficient, right? Now, the angle is called the angle of static friction. And for systems with impending motion, when they are about to move, and we can define F as F max as equal to mu s times the normal force, right? In those cases, the angle between the resultant force, contact force R, and the normal force N is always given by the angle of static friction. Now, one quick application of this concept, right, is the way that you could measure friction coefficients at home, right? Incredibly enough, right, the process is very simple using this particular result, right? So this is a block, right, a rigid body on an incline, right? Rigid body on an incline, right? So rigid body on the incline. And if you wanted, you could obtain the friction coefficient, right? You don't need a specialized machine or to measure the normal force or the weight, right, in order to determine the friction coefficient, right? We can do it using simple free body diagrams. So I take my rigid body, right, and I write the forces acting on it. So this is the angle theta, right? Right, and then the rigid body of the has this free body diagram. I see the friction force just aligned with the inclined surface, and the normal force just going exactly perpendicular to the sliding plane, right? And one may wonder, what are the angles, right? Because here there is a reaction force, right, oriented at some sort of angle, but we don't really know the angle, right? So how can the angle can be found, right? Well, we have to remember basic geometry of angles, and this is going to be very useful. So this is the angle I'm looking for, right? This is the angle I'm looking for, and you see it's defined, right? It's defined between the normal force N and the angle R. So how can you actually make sure that that angle exists? Well, right, if you remember this diagram from before, right? Let me just try to get rid of that one. Right, it's just an easy diagram that shows you where the angles are for an inclined plane, right? And you immediately see that for the angle that happens to be here, right? This one is theta, so this guy is theta, right? So this is just simple geometry. Okay, so if we started this experiment when the body was flat, and then you started picking this inclined plane like this, right? Inclined plane like this, and then you kept increasing the angle a bit, and you do that until the body starts sliding down, and you stop. What you just found is the angle of static friction. Why? Well, because the tangent of the static friction, right, angle, is equal to F divided by N, and then F is equal to mu times N, right? And then right, this cancels out, and then the angle of static friction is equal just to the tangent inverse of the friction coefficient. So if I want to calculate this guy, right, I just go and then I apply the tangent of the angle, right? Well, they're calling it phi, I'm calling it theta, but you get the idea, right? It's the same angle, right? So if I measure this angle and get the tangent of the angle, right? That guy is equal to the coefficient of the static friction, and I can go and write it on the table, right? And so it's a nice example of what I can do, right? So friction, right? This is the theory for friction. Let me just clean up this. So we solve for the angle at which the block first starts to slide, and once you have the angle, then you can get the tangent of it, and then you would obtain the coefficient of static friction. So, right, well, the value for the angle is called the angle of repose, and it has the same value as the angle of static friction. A very easy experiment to do at home to obtain coefficients of static friction. So summary of what we have learned in this video. The friction force opposes the direction of motion or impending motion. F is tangential to the contact surface, right? Tangential to the contact surface. F is independent to the contact area. It depends only on the normal force through the coefficient of friction. If F is less than mu s times the normal force, there is no motion. If it's equal, there is impending motion. It's about to move. And if it is equal to this, it's sliding, right? Equal to the kinetic friction coefficient times the normal force, the body is sliding. So we will not cover those cases in this course, right? And finally, we must check for the possibility of tipping or rocking, right? And a key part of that check will be to calculate moments, to use the moment equation, and to the moment equation when the normal force is right at the corner, right? Because that will allow me to rock the rigid body. So a few examples coming up, right? See you on the next video.